So in this question, you can think it this way. Type 2 error is when you cannot punish this company. You have to punish this company, but you may not be able to detect the cheating. And if the cheating is even more severe, like cheating by 0.2 pounds, then it would be easier for you to detect the cheating because the difference is larger than 2.9. So you should be doing much better. Then type 2 error probability will be decreased. So the answer is E, lower, right? Your type 2 error probability will decrease when mu is moving from 2.9 to 2.8. So if you do calculate, then the only difference is the standardization, standardize with different mean, and it will be about 36%. So larger lies are easier to detect. And power is just simply the flip side of type 2 error. It is the probability of punishing a wrongdoing company, right? And so because we already calculated the type 2 error probability as about 74% and 36%, 100% minus that equals the power. So when the company is cheating at 2.9 pounds, the punishment probability you can detect it, you can punish the company with 26%. But if it's 2.8, then you can do it even better, 64%, right? Power is maybe the always goes with type 2 error probability. Okay, here is the next example. This example is about Affordable Care Act. I don't put any political interpretation on this. I think it's a very good example to apply one-tail test, and especially for binary distribution case. So I am just doing this as an example. I don't put any interpretation, any political meaning or claim, or any like I'm value neutral. And by the way, I really enjoyed yesterday's election results. Watching the scores, how many, who is winning, who is losing. It was fun. I stayed late. I'm not a citizen, but it was still very fun. Anyhow, Affordable Care Act. I assume that. So let's look at the graph first. So in 2014, many years ago, Affordable Care Act took effect in all states. Simply, it is to improve the health insurance coverage in America, in the United States. So I will assume that we would like to test the effect of this Affordable Care Act. It is easy to it's easy to assume that this Affordable Care Act would not decrease the coverage rate. Coverage rate would not be lowered by this policy. So look at the data, for example. Before the policy, the coverage is about 48% by employer and 15 Medicare, about 18 Medicaid. And so in the end, 13% was uninsured. But after the policy, uninsured becomes only 9.9%. So it dropped by a little bit. And I'm wondering if this drop is the same, if it's significant or not. So I will consider an example based on this example. Suppose that P is the proportion of American adults who have health insurance. So for simplicity, I'm going to assume that that coverage rate is 80% in 2013, which is before the policy. Before the policy take effect, the coverage was 80%. And I would like to test this. The null hypothesis is that Affordable Care Act has no effect on the coverage rate, does not improve the coverage rate at all. And alternative is that it does improve the coverage rate. And as you see, as I said, I don't consider the possibility of low, lowering the coverage rate. The Affordable Care Act would not do any harm on coverage rate. That is my assumption in this testing. I think it's reasonable. So then let's compare whether it is the same or increased. That's the comparison. And I'm going to use 5% significance level. And suppose that you surveyed 100 adults after the policy took effect, and you found 86%, 86 of 100 had health insurance covered by an health insurance, right? Then how can you do the hypothesis testing? Remember, the tricky point here is the binary distribution. When you have a binary distribution, standard deviation is determined by the hypothesis or the population mean, the mean. So in this case, remember your hypothesis is that coverage rate would be 80% still after the policy took effect. So and then if your belief is correct, the probability is 80%, which implies standard deviation equals 0.4. So using this standard deviation, you can calculate the t statistic. So your sample mean is 86%, and you believed 80%. Coverage rate you believe in is 80%, and the coverage rate from the data is 86%. The difference is 6% point, and you standardize it by 0.4, which is the standard deviation of a single outcome, and divide by square root of n, or square root of 110. If you calculate, you get 1.5 plus 1.5. So you find that after the policy change, the policy increased by 1.5 standard errors. Is it significant? Is it something, or can it happen just by chance? We have to decide that. So I am going to calculate the p-value. What is the p-value? It's a good chance to practice. Okay, calculate. I already calculated the t-statistic, so you calculate the p-value. Remember, it's a one-tail test, and remember which side we are handling. And try this question and continue to the next one. Thank you. Thank you for watching this.